All right, so today's notes are on exponential models. Our content objective is to model exponential growth and decay, and our language objective is to describe exponential equations and graphs as modeling growth or decay. So first thing, an exponential function is a function in the form y equals a times b to the x, where a is not 0, b is greater than 0, or b is positive, but b is not 1. So again, as long as it has this form and meets these requirements, it's an exponential function. The reason these are true is because a can't be 0, because if a were 0, that whole thing would cancel and just be 0. B has to be positive, because if it had a negative value, it would end up jumping back and forth depending if it was an even or odd exponent. So if it was even, it'd be up here, then it would odd, it'd jump down below the x-axis, and it'd be a very confusing shape that wouldn't actually work out. So B needs to be greater than 0 and B needs to be positive, and B can't be 1 because that would just end up with a flat line. So again, these are only restrictions because you'd end up just with a graph that didn't have the same shape as all your other exponential graphs. So now jumping into what we're going to focus mostly on today, exponential growth and decay. So as you may have gathered from my referencing, these are both models of exponential functions. So these are both graphs that represent an exponential functions. And exponential functions can be categorized in two different ways, as either growth or decay. And they're categorized based on the value of the base. So base is, again, the b value here. So the base will decide if it's growth or decay. If b, the base, is greater than 1, then you will have growth or exponential growth, because your graph will be increasing as you go left to right. So exponential growth is when your graph is increasing from left to right. So since this graph is going up, you know that your base would have to be a value greater than 1. It would be growth. Decay, on the other hand, your base is between 0 and 1, or it's a fraction or decimal that's less than 1 while still being positive. And decay is when your graph is going down from left to right, or it's decreasing from left to right. So if you're looking left to right and it's decreasing, it's decay. If you look left to right, it's increasing, it's growth. And you can figure out if a equation will model growth or decay based on the base value specifically. So I included some examples here that can help you figure out what actual growth and decay functions might look like. So you could have y equals 2 to the x. Again, that base is greater than 1. It would be growth. 5 over 3, even though it's written as a fraction, 5 over 3 is greater than 1. So it would also be growth. Again, 1/2 times 3 to the x. 3 is the base. So that is what you're looking at. It would be growth. And again, 4 is the base. That's what you're looking at. It would be growth. So even though a is less than 1, that doesn't matter. You're only looking at the base value. The same is true with decay. So 0.2 to the x, that's between 0 and 1. That's going to be decay. 1/3, again, between 0 and 1, decay. 1/4, decay. 0.5, decay. Again, it doesn't matter if the a value is greater than 1. It's only the base value that you're looking at. So again, base needs to be greater than 1. Base is between 0 and 1. That's what matters. And we describe the base as either a growth factor or decay factor. So growth factor or decay factor depends on the base value. So you're only looking at the base, and so in this example, we'd have a growth factor of 3. In this example, we'd have a decay factor of 0.5. That's how you describe those situations, and we'll practice those some more in class. The last thing I want to talk about with growth and decay is modeling them. So we're going to try some application problems today. And we'll be using these two equations, which you may notice are identical, except for one is adding r and one is subtracting r. So in these modeling problems, this is the final amount, this is your initial amount, and this is your rate. The same is true here, final amount, initial amount, rate, time. Sorry, I also skipped t, that's your time. I also didn't write a is the initial amount. So the only difference here is that when you want to have model growth, you're going to add your rate or your growth rate, because you want it to end up being greater than 1. So notice how it's 1 plus the rate, we'll end up with a value greater than 1, whereas 1 minus the rate will end up with a decay factor or a value less than 1. So if you're trying to model growth, you add the rate. If you're trying to model decay, you subtract the rate. And we'll practice that some more in just a second. But for now, I'm going to flip the page so we can talk some more or do a quick check and talk some more about the graphs before we go into some final examples of modeling. So now that we've given the overview of the two categories, growth and decay, I want to spend some more time delving a little deeper into some of these little subsections. So the next one, our quick check. I want us to identify, or I want you to pause and identify these as either growth or decay. So I showed you 4 examples for each one. I want you to pause and try to identify these on your own. So are these growth or decay? Which one could be which? All right, so I'm going to go over it now. Again, you're looking at only the base value here. Since that value is between 0 and 1, it will be decay. So again, because your base is between 0 and 1, it's decay. Here, again, we're just looking at the base. This base value is more than 1. This would be growth. So decay and growth, just looking at the base value, the A value does not matter. It is just the base. So the next thing I want to talk about is our graphs before we do our last example together. So again, I told you exponential graphs usually have a form like this. It could go the other way if it were decay. But some of the key features we're going to pay attention to, and we'll spend more time with this in our next lesson. So we'll delve more deeply into exponential graphs next lesson. But for this lesson, I want you to pick up on a few key characteristics and features. So the first thing I want you to know is that it has an asymptote. And this is something we haven't talked in detail about yet, but an asymptote is a line that a graph approaches but never reaches. So a line that a graph approaches but never reaches. So as you can see on this side of our graph, it's getting closer and closer to our x-axis, but it will never actually reach it. And we'll talk about more about why later. But it will never actually cross the x-axis. So the x-axis in this situation would be the asymptote. So the asymptote is the line it approaches but never reaches. So in this situation, it'd be our x-axis, which is when y is equal to 0. So in this example, our asymptote is y equals 0. The reason we bring this up is because, first of all, that's a main feature of exponential graphs, but also it tells us our range. So our range will always be y is greater than the asymptote if it's up this way, or if it were going down like this, you would have y is less than the asymptote. So our range is always going to be y is greater than or y is less than the asymptote value. So that's why it's going to be specific or particularly helpful when we're describing our exponential graphs. The other thing is our domain is all real numbers. So again, there's no variable in the denominator. There's no square root or even root of x. So our domain is just all real numbers. We can plug in any x value we want, and we will never have an undefined situation. So that's it for exponential graphs. Last thing I want to do in this lesson before we wrap it up is a modeling problem. So again, the last part of our previous page talked about modeling exponentials. So in this problem, I say you've invested $1,000, or you invested $1,000 at the end of 6th grade in an account that pays 5% annual interest. How much money will you have at the end of 6 years? So again, we're using that formula or that equation that I showed you in the last page. Since I'm going to be earning money, my money will be growing in this account. I know I'm going to use my growth version, so I'm going to add my rate instead of subtracting it. I'm not losing my $1,000, I'm gaining money to it. So I'm going to add R. So now I'm just going to define my variables. I know my initial amount is $1,000. I know that my rate is 5%, which I will rewrite as a decimal. So again, you need to rewrite as decimal. There we go. So I needed to rewrite this as a decimal before I plug it in. And then the last thing is the time, and that is 6 years. So if I plug that all in, I get A of 6 is equal to 1,000 times 1 plus 0.05 to the 6. And if I simplify that, I'm going to end up, I would plug this into my calculator, and I won't show you plugging it into the calculator right now, but I get 1,000 times approximately 1.34 something, 3, 4, dot, dot, dot. So if I added these and raised to the 6th power, I'd get a decimal in my calculator. One thing I want to note is when you're doing exponential growth and decay problems, you don't want to round while working. You want to keep your unrounded answer in your calculator. So then I end up with approximately 1,340.0956. Since I'm talking about money, dollars, my final answer should be in dollars, which only goes to 2 decimal places. So I'd look to this place and I'm going to have to round it up since this is 5 or greater. So it's going to round to $1,340.10. So my final answer is $1,340.10. All I did was plug this in, add this, raise to the power, multiply, or evaluate this following PEMDAS, and I got my final answer. So that's it for today. Make sure you write down any questions, comments, or concerns you have so we can go over them together in class.